So just to remind you again, the Miri LRS is a double prism. It's mounted in the filter wheel, and basically you have two positions. You have a fixed slit that takes full array data. It's basically not used, of course, for TSO data. That's sort of in the middle there of the image. And then we have a subarray located to the left, upper left, which is a completely slitless spectrograph, solely used basically for the TSO observations. So all the TSO observations will have actually use this subarray data, which is sort of 72 pixels by 416 pixels with a frame rate of about 0.15 seconds. Next slide, please. And so I just jump right into our observations. So we observed a super Earth planet, so about 1.4 Earth radii, with a period of 1.4 days and a transit period of transit time of 1.2 hours. And here on the right, basically, I show you I mean, it's an amazing data set. Just to show you the data quality. Already, this is the standard rate-ins data product, which is also in archive, or it should now have this quality, and you immediately see the transit already in that data set at 500 ppm level. And the overall drifts basically show is extremely small. The average drift in the first 20 minutes or so, which you see there right in the beginning, is a bit higher, sort of 0.3% drift at most in this particular data set. And then over the rest of the 3.5 hours of the transit observation, we only see a drift at the sort of 400 to 500 ppm level. So it's very, very small for a mid-infrared instrument, and way smaller than any other data we have seen previously with other instruments. So next slide, please. And so basically that's actually just to remind you, that's sort of like first 20 minutes, and then it settles in a very, very slow drift, sort of leveling out after sort of 2 to 3 hours. Then you hardly see any drift anymore right at the end of this transit observation. Next slide. So just to say something about the processing we did. So this is sort of the stage 2, or sort of stage 1 processing. I basically followed, for the analysis I'm showing here, the sort of standard pipeline and steps. What is important, of course, that we had to update the input calibration files, which should now be in the calibration system. And actually, the data should have been processed now with the new calibration files. So I advise everybody to check that. And basically, we follow the basically standard pipeline, apart from we skip basically the first frame effect. So that's basically you can skip or throw away the first frame on the integration, because we only have 9 frames, so we don't do this, but we do throw away the last frame because that's not very easy to calibrate. And we skip the RSCD step 2, given that you normally throw away the 3 frames for absolute flux calibration precision. That's not needed for the TSO observation, so we skip that step 2. The only other thing the user might think about is to check a bit the jump step detection, and perhaps take a slightly larger sigma, especially if you have very short frames which might not be entirely linear, that you're not flagging too many pixels, or basically you're flagging perhaps a non-linearity on the ramp rather than actually in jump. But that's something you should just play around with and check. Next slide, please. The stage 2 processing, again, it's more or less the same. So what I didn't do, however, is the background subtraction standard with the pipeline, and we skip the photon step. So we don't do a absolute flux calibration here, we just do everything in dns per second. What we also did is follow a polynomial trace to extract the spectrum, although it's not strictly needed for perhaps for the Miri observations, because they have only a very small 1 pixel sort of offset over the few hundred pixels in the dispersion direction. But to be absolutely certain we don't get any effect there, we determine the polynomial of the trace and use that in the spectral extraction with an 8 pixel wide extraction. Background we subtracted using a median background based on several pixel or detector rows, detector columns next to the source. And then we did some additional filtering to detect any remaining cosmic hits. And basically that's an important step, which is not standard in the pipeline yet, is if you have bad pixels or flagged pixels, that you of course have to correct them before doing an aperture extraction. So that was one of the additional steps done to the data set. Next slide, please. So this is then how it looks like. So this is then the spectral trace. So you can see, so it spans about 400 pixels. So you can all the way see the trace up to like 14 microns. So the nominal wavelength range for the LRS is 5 to 10 microns, but I think it's useful, at least for the TSO observations. You can certainly go up to 12 microns, I think. You still have enough signal to noise there, especially for the brighter targets. Like I said, you can use a spectral trace here, but it's only 1 pixel in the cross dispersion direction. Next slide, please. So this is just a bit about the actual PSF and the image quality here. It looks very pretty. So on the left here, I just showed the full array, so for the slit actually. So in the middle panel, that's a bit a zoom in of that. And on the right, it's actually the slitless subarray, so it is used for TSO. And what is most important here is for people to notice that at the very short wavelength range, so from top to bottom, basically you go down or you go up in wavelength. So the edge there is around 4 microns, and then going downwards is towards 14 microns. That at the short wavelengths, we see some detector scattering. So what Nestor already mentioned in the previous presentation is that for Miri detectors, we also see additional photons, which is basically scattered in the detector and then absorbed in nascent pixels, basically, from where actually the source is. And that does give a sort of this cross pattern here on the detector. You also see it, of course, in the imager. So if you just have a nice image of a point source, but of course you also have this in the slitter spectrograph. The strongest effect are at short wavelengths, so longwards of say 7-8 microns, there is hardly any effect anymore. But sort of the 5-6 microns, you see the strongest effect, and that does give an additional noise in your observations. And of course, you have to take care about this when you do background subtraction, or if you want to do PSF fitting, for instance. Next slide, please. So this is then the result. On the left, you see basically the white light curves, so integrated over the 5 to 10 micron band. So the top panel there shows the uncalibrated white light curve plus the systematics model we fitted in black. Then the middle panel shows basically the corrected white light curve plus the fitted transit model, and on the bottom panel there is then the residual between the observations and the light curve fit. And here on the right, you show them basically the result of the spectrum, which is consistent with just a flat spectrum as expected. at around 530 ppm, which is in perfect agreement actually with the test measurements. So that's really within 1 sigma. This is actually on a resolution of 50. So we binned here to about 6 pixels, detector pixels at around 7.5 microns, that scale. But yeah, exactly. Thank you. So on this panel, I show you the overall transit depth. So based on the white light curve of about, like I said, 530 ppm, with an about 1 sigma error on that, about from 10 to 15 ppm. So very precise measurement. And on the right here, I showed the error, the measured error, derived error on our transit spectrum, sort of at the 7.5 micron region of about 40 ppm. And we did do a performance test actually. So if you go to the next slide. So what we show here basically is in blue there on the left panel is the actual observations. This is now the spectrum. So this is one of the observed spectrum in the spectral time series compared to a simulation of the data using the in-orbit measured spectral response function using the Miri simulator. And so that agrees very, very well. We use this basically to get an estimate of the Poisson noise in this data set, and then I made a simulation using that noise of the transit observation. So no systematics, just now random or the expected random noise, and did a fit again. And if you then go to the next slide. So that's again this figure that now the solid line is then basically the noise floor estimate. And basically we're very consistent with that. There's a thing missing. I just want to show you that actually on the very short wavelength end, so on the 5 to 6 micron, actually, thank you, Nestor, pointing that out. That's probably due to this detector scattering effect, that we have an excess noise which is not actually currently properly modeled in the Miri simulator, at least not the exact level what we see in the data. So that is a bit higher there, but the actual noise level is way better, but it's better basically than we originally estimated for the ETC pre-flight. So that's good news. And so we're in overall performing better than expected. This is just quickly on the pointing stability. So we have, of course, we have a larger pixel scale, so we're slightly less perhaps sensitive also to these issues. But during our observations on the left, I showed the FGS data, and the orange line is then rebinned to the actual integration times of the Miri observations. And the only effect we see was a high gain antenna move around 0.4 in the on the left figure, and which was could also be seen in the Miri data exactly, that you saw a small movement, but that was only a handful of integrations, and you can just remove those integrations. That has no effect whatsoever on the overall results. And for the rest, we could detect, certainly not in the Miri data itself, any pointing movements or drifts or anything like that. Next slide, please. One thing I think I should point out here is that we do see a systematic noise in the Miri subarray data. So that might actually be for all subarrays, especially if you have, for bright source, very short integrations. So only if a few frames per ramp. You might see this, that we have a sort of periodic signal that's in DN in the data. It's very low level, but you can see it. So what I plotted here in the image is in the y-axis, basically is the median spectrum for the background. And then on the x-axis is then for each integration. And already you can see this by eye, this sort of pattern appearing. And if you then do a Fourier analysis, you clearly see some frequencies. So in time, you get the sort of 4 integration periodic signal here. In wavelengths, you get the sort of 9 pixel wave, which goes sort of move sort of through your data. But it can be very efficiently removed if you determine your background per integration and then subtract that background per integration. And then basically all of this will be gone. So that's an important thing to do, that you do a per integration background subtraction. So next slide, please. And so that's then brings me to the summary. So we can clearly say that it's performs well, extremely well, like the other instruments. We have a better sensitivity than we had with the current ETC estimate. So we'll need to update this, so the user will get a better quality data. By the way, it's slightly higher throughput, etc. But we determined this has no impact on the saturation limit, for instance, for the data. We checked that, and the ETC had already had quite a conservative limit there, and that will not affect the actual data. So we're quite good there. So you will get. We don't expect the user to have to change anything about the setup of the observations. You simply will get a higher signal to noise. Pipeline, I think that is actually works very well, especially with the now first in-orbit measured calibration files. So most of it can be used already for the analysis. We have to do a bit more work on the spectral extraction, especially for bad pixel correction. Of course, there might be one update for optimal extraction type thing, that it might not be strictly needed anymore. But these are only minor things, and will be added, I'm sure, to the pipeline in the near future. And like I said, so the achieved noise level in the 5 to 10 micron region is sort of at the 40 to 50 ppm for a resolution of 50 at 7.5 microns. So that concludes the Miri presentation.